Hello, my name is Angel Grace Tita Rocas, and I will be discussing the last property of Laplace transform, which is convolution. So before anything else, I would like to do some simple recall about the topics we had last semesters. So Laplace transform. In this example, we have function y of t, and when you do the Laplace transform, it is then denoted as a capital letter y of s. And when you do the Laplace transform, you multiply e to the negative st, then integrate it from 0 to infinity. Moving on to the convolution, it is denoted by a star, and it is also an operation, a mathematical operation, just as multiplication, addition, and integration. The convolution of two-time signals. Convolution is a mathematical tool for combining two signals to produce a third signal. In other words, convolution can be defined as a mathematical operation that is used to express the relation between input and output of an LTI system, or linear time invariant system. These are the properties of convolution. It is commutative, distributive, and associative. Please take note of these properties while solving. Some mathematical problems have very lengthy solutions. Convolution, when done right, is a powerful tool to simplify your solution. Right now, I will give you the proof of the convolution theorem, and I will show you how this equation is derived. When you take the Laplace of a function, you will multiply it by e to the negative st, and the product obtained shall be integrated from 0 to infinity with respect to time. Since we are dealing with the convolution of two functions, we will plug in the definition of the convolution, which is, for this example, f of t minus tau multiplied by g of tau d tau, evaluated from 0 to t. So right now we are dealing with double integrals. When dealing with double integrals, it would be best if both of their integration limits are the same. And how do we do that? The other one is 0 to infinity and the other one is 0 to t. So there's a way to match those integration limits. We can utilize the unit step function u of t minus tau and change the integration limit, which is 0 to t initially, to 0 to infinity. Now, this may look different to the original expression, but it still yields the same result because when you graph this, it will still give you the same area. Right now, it would be best if we choose to evaluate the function with respect to time first. Now, for this, everything that's not in t should be treated as a constant. So, for example, g of tau should be treated as a constant and can be put outside of the integral. So, evaluating with respect to time, notice that the red colored expression is just the Laplace of f of t minus tau, u of t minus tau. So by looking at the table from the previous chapters, we can get the answer e to the negative tau of t multiplied by f of s. Now that we are integrating with respect to tau, we will take f of s outside the integral. Now, same thing that happened earlier. We're just taking the Laplace transform of the tau function. The answer will be g of s. Now that's how these equations were derived. To further understand this property, I will give you an example. Obtain the Laplace transform of the convolution of two time signals. The first signal, x sub 1 of t, is u of t plus 5. Then x sub 2 of t is Dirac of t minus 7. To obtain the final answer, we will take the individual Laplace transforms. The Laplace transform of x sub 1 of t is multiplied to the Laplace transform of x sub 2 of t. Referring to the table from the previous chapters, we know that the Laplace transform of u of t plus 5 is e to the 5s over s, and the Laplace transform of Dirac of t minus 7 is equal to e to the negative 7s. Now, the final answer is the product of these two, which is e to the negative 2 of s over s. That is our final answer. Thank you for your patience. God bless and good luck.